Hello friends, welcome to ACE Engineering Academy online platform where we are going to discuss GATE 2022 questions from the data structure. Before I begin, I'll just show you some analysis of GATE 2022 question, and this is a question type analysis. The type MCQ, MCQ still leading the way that there are 22%, 22.4 percent question from this MCQ. MSQ is 15% of the question from MSQ, multiple select choice question, MSQ, and here in this case is NAT is 18%. So quite interesting here in this cases, but still leading is your MCQ questions are larger in this. These are the different weightage of marks here in this year, and here we have the data structure is only the number of question that ask here in this case only 5 marks questions is asked from data structure. Okay, and in this case we have another one that is programming, which is right now separately written, and only 6% of the question asked from this programming. Let's discuss the question from data structure, and this is the first question from the data structure from 2022, 1 mark question, and it is a multiple choice question, MCQ. Consider the problem of reversing a single linked list. To take an example, given the linked list below, where head is given to you A, B, C, D, E, and we want to reverse the entire linked list by E, D, C, B, A. The reverse linked list should look like. So this is how the reverse linked list should look like. Now, which of the following statement is true about the time complexity algorithm that solves the problem in order of one space? Okay, time complexity which solves the problem in order of one space. Now here it is clearly mentioned that you are only supposed to use order of one space. That means you can only use variable, okay, variable and constant. Okay, this is the only thing that you can use, that is you are allowed to use, because it is mentioned that you have to solve the problem in order of one space. Options are: the best algorithm for the problem takes theta of n time in the worst case. The best algorithm for the problem takes n log n time in the worst case. The best algorithm for the problem takes n squared time in the worst case. It is not possible to reverse a single linked list order of one space. Reversal of a linked list, reversal of a linked list, and generally this problem we always cover in the class, and this is the algorithm for reversal. Where we are having a node declared in this case. We have a node declared, and the type def is also there. So we have this here in this case is struct node, and we have in this case is link is there, and I believe data is also there. So int we have a data, whatever this, and we'll say that struct node self-referential struct node star, and I'll write here in this case is link. Okay, and then I will call this the entire thing as, you can write as node, and you can write here in this case is type def. Okay, so this is a typical way of writing linked list code, and in this we have link and data. Now, so now here we have only, like here, can you see any other variable? There is no n, nothing is there, just a pointer is here in this particular case, right? Only pointers. So here in this, for reversal, we have node double star t, pointer to a node, and then we have 3 pointers declared, and in this case is q is equal to star t, and we are running a loop here in this cases. Now, to understand it in a much better way, please have this notion of, or this 1000 is the node value 1, then we have this link to 2, and suppose this is 2000, so I'll write the value 2000 here in this cases, and suppose the next value in this case is 3, and this value here in this case is null, and suppose this is 3000, and in this case I'll write the value here as 3000. Okay, we will maintain a head pointer HP, and there I will hold the value 1000, and now we are sending this address 4000 double pointer. So this HP is a pointer to a node, and I'm sending address of that pointer. Okay, HP itself is a pointer, and that address I am sending, and that will be stored here in this case is double star T. That will be stored in this case is double star T. So double star T is equal to, in this case, is what does each thing represent? Now if I say T, so now T is another double star T is a node variable which will contain the value 4000. Look at this. Now when you say only T, T value is 4000. When you say dereference T, one more time dereference, then it will give you 1000. If you say double dereference T, then it will go to this particular node. So T is 4000, single time dereferencing of T is equal to go to the 4000, 1000, and one more time dereferencing, then you will reach to the node. Okay, now things are very simple in this cases, that Q is equal to dereference T. So now Q will contain dereference T. Star T value is what? 1000. So it will now Q will contain 1000, and while R is null, so Q is pointing to this, Q node is pointing to this, and R is pointing here in this case is null. R is pointing to null. Now, while Q is not equal to null, S is equal to R. So now S is equal to R, S becomes null, R is equal to Q, R comes here, and Q is equal to Q pointing to link, Q is equal to Q pointing to link, and R pointing to link is equal to S, and that means here in this case, I'll take this link out, and I'll point here in this case, this link to S, which is right now null. S is right now null. Done. One pass is completed. Q is pointing to null? No, Q is not pointing to null. Then again it will be S is equal to R. S is equal to R. So S will move forward here. S is equal to R. R is equal to Q. R will come here, and Q is equal to Q pointing to link. Q will come here in this case. And again it will say R pointing to link is equal to S. This link will be destroyed. Okay, this link will be destroyed, and I need to update the value as well. Okay, I need to update the value as well. So here this link will be destroyed, and in this case I'll take one more point in this. Okay, now here this is null. When it was null, this value will be no longer 2000, but it will be null. This value will be no longer 3000, but this will be R pointing to link is equal to S, and which is right now 1000. One more time, S is equal to R, S will move here, R is equal to Q, R will move here, and Q is equal to Q pointing to link. Q will become null in this case, Q will become now null. Okay, Q pointing to link is null, and R pointing to link will be equal to S, and this time this will point here in this case, and this will be no longer null, this will become 2000. And finally, star T means this star T, which this location, this head pointer which is now 1000, will now be updated with the value in this case is R, and R in this case is 3000. So finally this will be also gone, and in this place what will come in this case is 3000. Okay, so this is the reversal process. How long I will take? So this journey will start from the head pointer and go till the last node, and we say that we had traversed the entire link, and each time we are doing some constant number of operation. This is not even taking the entire linked list as the input as well. Okay, so here only the pointers are there, and with using this pointer I can reverse the entire linked list, and in this case I can say the best algorithm for the problem is the best algorithm for the problem solve the problem in theta of n time in the worst case. A is the answer for this question. Okay, A is the answer for this question. The next question is from GATE 2022, is 1 mark question, and it is a category of again MCQ, multiple choice question in this case. Now suppose we are given n keys and m hash table slots. N keys are given to you and m hash table slots, and two simple uniform hash function h1 and h2. Okay, so there are n keys and m hash tables, and in this case two simple uniform function h1 and h2. Further, suppose the hashing scheme uses h1 for the odd keys and h2 for the even keys. So now here this is using one for the odd keys, another for the even keys, but it is saying it is uniform in this particular case. What is the expected number of keys in a slot? What is the expected number of keys in a slot? Now the expected number of keys in each slot, okay, expected number of keys in each slot termed as load factor. Okay, now already it has been said that the keys are distributing uniformly. Okay, so whether whatever the keys that it is coming for odd or even, it has nothing to do with that. Actually, it has a uniform distribution over the keys. So the answer for this question is this particular question. It is not going to depend upon, in this case for this h1 and h2 actually. What is the load factor here in this case is that what will be the length here in this, what is the expected keys in a slot. So in this case average keys in the slot, m slots n keys, so n by m. So now we have 10 slots, 25 keys are there, 25 25 keys. Okay, 25 keys and n slots, suppose n is equal to 10 and slots are here. Okay, in that case it will be 25 divided by 10. So in this case given n keys, so n and m hash table slot, so n by m. Okay, answer for this question will remain as b, n by m, because whatever hash function you use, the slots are basically in this case will be mapped uniformly and it will not going to depend on them. So answer for this question is n by m. B is the answer for this question. Let's move to the next question. The next question is from GATE 2022 and it's a 1 mark question. Okay, it's a 1 mark question and the question category in this case is NAT, numeric answer type. Okay, so the question category in this case is NAT, numeric answer type, and it says that suppose a binary search tree with 1000 distinct elements is also a complete binary tree, CBT, complete binary tree. Now, what is a CBT? CBT is a tree where all the levels are full except the last. Okay, and the last level also elements are filled from let's say in this case left to right. So as much as, and no place is empty, and CBT is one of the very common concept that we use in case of heap, CBT, complete binary tree. So suppose the binary search tree with 1000 distinct element is also a CBT, complete binary tree. The tree is stored using the array representation binary heap trees. So we use the binary heap tree representation and with that it has been used. Assuming that the array indices start with 0, the third largest element of the tree is stored at index. The third largest element that will be stored in the index. Now first of all about the CBT, complete binary tree. So now here in this case you can have this as a CBT structure. This is a CBT structure. I'll go one more level here in this case. Okay, now this is one more level I will go. Okay, so this is a CBT structure. Now this is a CBT structure as well as this is a full binary tree. Now, what does the CBT says that we want, okay, last level may not be full. So even if you take out some element, take out this, if you just cut the, or you prune some branches here in this cases, then even if you cut the branches, then also this is a CBT, the except last every level is full. This is the representation of this. Now, we have 1000 distinct element in this particular case, 1000 distinct element, okay, 1000 distinct element, 1000 distinct elements, right? So that is we are having in this case is 1000 distinct element. If we have the 1000 distinct element, and if I ask you is like here, I'll come to the 1000 part. But here, if I just ask you that what if it is a binary search tree, okay, if it is a binary search tree, okay, as well as heap CBT, binary search tree, where is the largest element? 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 So in this case, the largest element is at this. Is it the rightmost node is the largest element? So this is the largest element here in this case, largest element. Okay. Now if it is the largest element, which will be the second largest element here in this case, right? Which will be the second largest element? So second largest element will be this, because it's a binary search tree. So this key will be greater than this, and this key will be lesser than this here in this case, but greater than all this, all the nodes previous to this. Okay, so this is a largest element, second largest element will be this, and this is lesser, that's why it is here, and this will be in this case will be your third largest element. Okay, third largest element. And one more intuition for saying this, that I know BST in order traversal, when you do BST in order traversal, then left root right, that is the how it comes. So when you come to this particular node, then you'll go to the left, then root, and then right. So suppose this is A, this is B, and this is C. So definitely left root right will be A, B, and C, and that means A, C is the largest one, second largest, and third largest will be A. That is this location is the third largest. The problem here in this case is what is the index of this location? Now if it is consist of 1000 element, 1000 elements, if there are 1000 elements are present, so definitely this tree is not a full tree or strict binary tree, sometimes other books call it. It's not a full binary tree, right? It's not a full binary tree. Okay, now why it is not a full binary tree? Because here the full binary tree, I'll just write the value 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and I'll go up to 2 to the power of 9. Okay, and here if I do this summation, means all the level up to height 0, height 1, up to 9 height if you'll grow binary tree, then it will be first term and 2 to the power 10 minus 1 and divided by 2 minus 1, and that is equal to 1023. So now here we have if it is a full binary tree, then it will have 1023 element over there. Okay, 1023 element over there, but we have only 1000 element over there. That means the last level is short, for it will fall short. Now you can also go into that detail also, how much it will fall short. But in that like 2 to the power 9, and that is 512, it will not be there. But here previous level will have 256 node will be there, 2 to the power 8, 256 node will be there. So this, and suppose I am more interested here in this case is the last one. Okay, the last 2 node here in this case. Suppose this is 2 to the power, that is 256 node. Okay, so definitely the last level 23, because here up to here it will be in this particular case 23 is shortfall. Okay, 23 shortfall, so definitely this will not have any edge here in this case. This will not have any children for this one also, for this one also, because if it is the children there will be 2, 2, 4, and 4 if I do minus here 20 in this particular case, then also it will not become 1000. So there are many such nodes will be there which will not have any children. Okay, so now here in this case this will have some children, that will also go into that part also, but there is not required. Okay, but here last two node will not have any children. Okay, so now it will be growing this up to 9 up to 8 length, up to 8 height, it is okay. The last level will not be full in this case, and here in this case each one it will not be full, and definitely this 2 node will be not further having any children. If it is not having further any children, then definitely what will happen in this particular case is that this is my largest element. This is my largest element here in this case. This particular element is the largest one. Okay, this is the largest one. Okay, and this particular one is the second largest. Okay, second largest. Okay, and this one is your third largest. Okay, this one is your third largest. Now, I can say that up to the previous level, how many elements are already been arranged. So in this particular case, I accept the up to this, everything is full. Previous level, everything is full, and that will be 1 to 2 to the power 8. So now the element that you have already arranged up to height 8 will be equal to what? 1, 2 to the power 8 plus 1, that is 9. Okay, 9 minus 1 divided by 2 minus 1, and that is equal to 511. Okay, 511. So now up to here 511 has been arranged, but the indexing start from 0. If indexing start from 0, okay, indexing start from 0, and binary tree representation, heap representation will index in this way: 1, then 2, then 3, then index comes to 4, then index come to 5, then 6, and then 7. So that order indexing has been done. So now if the indexing starts from 0, then definitely the last one that we are talking about, the largest element, this will have an index of 510. Okay, this will have index of 510, and just previous to that, okay, just previous to that, the index will be what? 509. Okay, 509, like this is 7, this is 6, 509. So this is your third largest element, and it is asking the index of it. Definitely the last level is not full, and index for this will be 509. 509 is answer for this particular question. Okay, answer for this particular question is 509. I'll give you one problem here in this case, is that you try to find out index of the second largest element. That will be quite interesting, because here in this case is just like 511, you will get, okay, fine, do it here in this case. Try to find out the index of second largest element, and with this same logic you can find that also. So hence here in this case is we have the problem, the index of the third largest element will be settled here in this case is 509 will be the index here in this. 509 is the index of the third largest element. The next question here is from 2022, 2-mark question, and its category is NAT, numeric answer type of question. Now here the question says that consider the Q1 containing 4 elements and Q2 containing none, shown as initial state in the figure. 4 element and Q2 containing none. The only operation allowed on these two Qs are NQ, Q comma element, and DQ. The minimum number of NQ operation on Q1 required to place the elements of Q1 in Q2 in reverse order. Okay, we want to put the element here in this case is a reverse order shown in the final state of the figure without using any additional storage is. Okay, so we want to reverse this Q and we want to put it into the second Q, and for that how many NQ operation, okay, what is the question? The minimum number of NQ operation on Q1, okay, on Q1 required to place the element of Q1 in Q2 in reverse order in this case. 1, 2, 3, 4, and this is the final here in this case is state 4, 3, 2, 1. Now, So the initial state is given to you here in this case is 1, okay, 1 2 3 4, 1 2 3 4, and I want to produce a list which is 4 3 2 1, and that is the in the final state. Okay, so final state I want to produce this particular list. Now what I can do here in this case is, this is one of the trickiest question I believe asked in the examination. But here we can like here, do not assume that elements are not shifted and all other things. Assume that this is a queue, circular queue I am assuming in this case. So I'm not bothering about the arrangement and which element is which element is. It's just a circular queue. Okay, and each and every space is utilized. So what I'll do here, I'll just delete 1 and delete 2. So I delete 1 and I'll put into this, delete 1, I'll put here, and I delete 2 and I'll put here. Okay, I perform 2 times DQ on Q1, and with that element is left here in this case is 3 and 4, and I'm assuming that it's a circular queue, so position wise let's say here only 3 4. Okay, so 3 4 element is here in this case. So I deleted 1 and 2 and I push that element in this cases, and that is 1 and 2. Now the question here in this case is, can I this 1 2 can I reverse the queue, that is without using any other thing? Can I perform the reversal? Okay, so now I can take out this one element. Okay, I can DQ and again I can NQ here in this case. Please do not bother about this position, that can be adjusted and considering the circular queue property. So now what I will do, I'll try to reverse the content of this particular queue, and that I will do here in this particular case by taking out this one and putting it over here. Okay, so now here so now here we have 3 4. Okay, 3 and 4, and in this case I'll take out this 2 1 and I'll make the queue in this case is 2 and 1. Right, now here in this cases again what we'll do, we will DQ 3 from this, we'll DQ 3 from this, and that will remain the value in this case is 4, and I'll again NQ here in this case, NQ here, and now the value will become 2 1, and in this case is 3. Now again I reshuffle the queue here in this case. Now I'll delete 2, okay, and then I'll put the value again here in this case as in this particular case as 2 1 3 is there. Okay, and I'll keep on deleting 2, keep on deleting 1, and I'll again insert it here. And please for the time being, because it's a sort of algorithm, do not look in terms of implementation point of view. I'll delete 2, I'll delete 1, and I'll again insert it in terms of in 3, and that will make here in this case the content remaining here 4. And what I'm saying is that I'll delete 2 and again reinsert into the queue, delete 1, again reinsert into the queue, and that will make the value as 3. I deleted 2 and I deleted 1. So now this will become 3 1 2. So now 2 deleted, that will be gone. So the element that will remain in this case is 1 3 and then 2. Then again I delete 1 and I delete again I push it back. So this will become 3 2 1. Okay, so please consider the programming as here in this case is all is been taken care of. So now this we deleted 1 3 2, and then we deleted 1, we again push it back, so that will come 3 2 1. Okay, and we deleted 2, then put the 1 3 2 and then 3 2 1. So final content is 1 3 2. Again I delete this here in this case is 4, and I'll put the value as 3 2 1 and 4. Now here I'll delete each and element from this because this is the head of the queue. I'll deleting 3 2 and 1. So I delete 3, the sequence will become 2 1 4 and then 3. Then I again delete 2, the sequence will become 1 4 3 2. Then again I delete 1 and the sequence will become 4 3 2 1, and that is the final sequence that we wanted. And in this particular case, this is the final sequence 4 3 2 1. Now question is, how many DQ operation and NQ operation we have performed on Q1? Okay, so answer here in this case is, we started with 1 2 3 4, then we deleted 2 times DQ, 3 4 remains 2 1. We reversed somehow, in this in place, in this we reversed this, taking out 2 and then putting it 1, making it 2 1, making it 2 1, and then again we have taken out 3 and again we put it over here, again we deleted 2 and 1. Okay, and then make space has been made 1 3 2, and then 3 2 1. Again we have deleted 4 from this, okay, and insert into this, and then the sequence 3 deleted putting in the end, 2 deleted putting in the end, 1 deleted putting in the end, 4 3 2 1. We finally achieved this sequence 4 3 2 1 in this. Answer for this question is 0. We don't need any NQ operation in Q1. That is the 4 question asked from this particular topic, and these are the answers for this 4 question in GATE 2022. That's all for the discussion from my end. I hope you enjoyed this session. Thank you very much.